If you are new to the channel, then subscribe the channel and press the bell icon for further notification. Okay student, welcome you all to this new lecture in meshes series. So again we will be solving 5 questions, question number 71 to 75. Okay, then let's try to solve these questions. So if you come to question number 71, the efficiency of a 100 kVA transformer is 0.98 at full load and as well as half load. Okay, for this transformer at full load, the copper loss is how much? So if you take full load, that is output by output plus, if I take constant loss K and copper loss C, that is given 0.98. And in case of half load, it is output by output plus, because it is half load, so it will be output divided by 2. The output divided by 2 plus constant loss remains same. Now what will be the copper loss? Because if you reduce your load by half, so copper loss will be reduced by 4 times, because it is I square R. So it is load copper loss is directly proportional to I square. So if you reduce it by half, so copper loss will reduce by 4 times. So it is given 0.98. If you solve from these two, here K plus C will be equal to, or into 0.98 equal to 0.02 output. OP I am writing output power. And here 0.98 into K plus C by 4 will be equal to 0.01 into output. So if you divide these two, you can find a relation between K and C, full load copper loss and constant loss. K plus C by 4. 0.02 by 0.01. If you solve it, you will find your constant loss is half of this. So full load copper loss is 2 times the constant loss. So which one is greater? Obviously copper loss is greater. So the transformer, the copper loss will be more than the core loss. That is your option C. And it is nearly 2 times. Now if you come to 72, the magnetizing current in transformer is reaching. So we have already discussed in harmonic restraint protection of transformer. You can find it there. To limit that magnetizing inrush current, we would that harmonic restraint. Because your harmonics, that magnetization current is very rich on third harmonic. That's why that harmonic restraint coil we use. So it is rich in third harmonic. It is always odd order harmonic and third order harmonic. So 72, it is A. In question number 73, a 50 Hz transformer having equal hysteresis and eddy current losses at rated excitation is operated now at 45 Hz and 90% of its rated voltage. So frequency also reduced, voltage is also. Compared to the rated operating point, the core losses under this condition. Initially both were okay. Hysteresis loss, eddy current loss, they are having equal. Now they are operating in this position, then what should be loss? Okay. So if you take your hysteresis loss, suppose H1, and eddy current loss, suppose E1. Okay. You know your hysteresis loss is directly proportional to, and your eddy current loss is directly proportional to Y square F square. But it is proportional to your V by F. So we have seen this one, and here it is proportional to V square by F square into F square. That is eddy current loss is proportional to your V square. So your H1 by H2 will be equal to V1 by V2 to the power 1.6 into F2 by F1, because with F it is inversely proportional by 0.6. And here eddy current loss will be equal to E1 by E2 equal to V1 by V2 whole square. So H1, H2 you don't know. What is V1, V2? They have given. You have reduced it, the voltage at 90%. So if it is 100, now it is 90. And F2 is equal to 45, and where F1 is equal to 50. So if you do this one, your H2 will be equal to 1.9 H1. And here also it is equal to 100 by 90 whole square. So E1 will be equal to 0.81, E2 will be equal to E1. So what is the reduction? Initially, what was the copper losses? Your core losses, E1 plus H1. Now what will be the core loss? E2 plus H2, which will be equal to 0.9 of H1 plus 0.81 of E1. And initially they are both equal, E1 and H1. Suppose they are equal to X. So it was 2X, now it is 1.71X. This is X, this is X. Because initial case both were equal in the initial rated values. Because you have reduced, now that's why it is changed. So what is the change now? 1.7 of this one. So what is the reduction? So from 2x to it is 1.7. So the reduction is 0.29x out of 2x. So in 100 it is how much? So it is 14.5% reduction. So that is your option C. 74. The winding of Q kVA V1 V2 volt 3-phase delta connected core type transformer was reconnected to work as a single phase transformer. The maximum voltage and the power rating of the new configuration. So from this delta you are now connecting it as a single phase transformer. reconnected. So this is your so suppose this side is also delta. So now you are opening it. So this winding, now this one, second winding will also be connected. This third winding will be also connected like this, because you are now connecting in single phase. So initially, if this is supposed to take V1, so it will now can withstand how much voltage? This was supposed to withstand V1 volt. So this is V1, this is, so total voltage it can withstand 3 V1. So in the secondary also it can withstand 3 V2. So your ratio will remain same. So that is V1 by V2. Current, it was able to take I current. Now same I current it will take, because now it is connected in series, because you are making a single phase transformer, so only one phase is there. So current remains same. Whatever the maximum current it was allowing, same current it will allow. It will not allow more current, because it is the same winding, same line only. But voltage it can withstand more. Initially this much voltage if V1, so now this 3 V1 can, because if you give 3 1, then V1 will come here. It will be divided equally, because all are of same winding. So voltage rating is increasing, but current is same. So your KVA rating will be 3 times of the Q1, because it is voltage into current. Current is remaining same. V is increased by 3 times, but current is same. So VI will increase by 3 times. So it is 3Q, but ratios of voltage will be V1 by V2. That is option A. Okay, in question number 75, what is asked? A 10 kVA 400 by 200 single phase transformer with 10% impedance draws a steady short circuit line current of. So if it is a steady state line current, so this is your transformer. That means short circuit means this is short circuit. So if I refer everything to the primary side, so this will look like this. So what should be the current it is taking? So this Z is referred to primary side. So what will be the actual value of this Z? This Z will be equal to 10%, that is 0.1, that is 10 by 100, into this side. If I am referring to primary side, so what will be is base Z? It is kV square by MVA. That is 400 V square divided by 10 into 10 to the power 3. So which is equal to 1.6 ohm. So this side it is 1.6 ohm if you look from this side. So your supply is here 400 volt. If nothing is given which side is supply, so you always take this is supply side. So what will be my current now? Because short circuit current, this is 400 volt divided by 1.6. So it is 250 ampere. So that is your answer. That is option C. If you like the video, then press the like button and please give your valuable comments in the comment section.